not lecture actually. This is in last practical we have discussed about the uh, parallel bubble sort algorithm. That is the odd even bubble sort algorithm. We have discussed with the help of example as well as we have discussed the program also. If you see there, and also we have seen the pseudo code of that algorithm in last practical. So second part of the same assignment, that is the B part, that is the merge sort. As already we have seen the bubble sort. Now today we will see the parallel merge sort algorithm. Okay, so you should able to design your own parallel merge sort algorithm from a given sequential merge sort algorithm. If you see there, using the that is the suitable parallel construct at the appropriate places in your program. Okay, if you see there, whether to use the that parallel construct for loop, or whether to use that parallel construct for a you can say the as a section. Okay, it depends on you. Okay, so there will be different choices for you if you see there. So I think as far as merge sort is concerned, you can use the hash pragma OMP parallel sections. Okay, that is the another parallel construct you can use here, like a hash pragma OMP parallel for, that is for loop, and this is for hash pragma OMP parallel for sections. You can use, means it will be limited to that particular section, or that particular section having the recursive or iterative you can say the call if you see there. So that section will be executed in a different iterations if you see there recursively. For that purpose, you can use the section if you see there. So we'll see when we'll discuss about the uh, program of the merge sort. But before that, we'll see example if you see there. So in case of the parallel merge sort, how it will work there. So logic here will be, that is the you have the that is the n number of elements in an array. So you can divide that array in two equal partition, that is the left partition and right partition if you see there. Okay, in first step. Okay, and you can apply here you can say the recursive divide and conquer algorithmic strategy if you see there. So that left sub part will again divided into two sub part, and right sub part or partition will be again subdivided into two sub parts if you see there. So this process will be continued until the that sub part is too small, or it is a individual element of that particular array, and finally you can that is the perform the combined step, and you can that is the combine the results of these partitions if you see there, from the left partition and from the right partition if you see there. So that will get the final result as a sorted array elements in a proper sequence, either in a descending order or either in a you can say the ascending order if you say that. So one example we have discussed here regarding the uh, parallel merge sort using the divide and conquer algorithmic strategy. So we have taken only 4 elements in an array, that is 6, 2, 9, 3. This is the given array. So in first step you have divided that array into two parts, that is the if you see there your index is starting from the 0 to 4 if you see there, or 1 to you can say the 1 2 3 4. If you are starting index 1, that is 1 2 3 4, that is 6 will have the index 1 and 3 will have the index as a 4. Then mid equal to you can compute the mid there, mid equal to that is the I plus j divided by 2, that is the 1 plus 4, that is the 5 divided by 2, that is the 2.5, means 2 will be the midpoint there, which if you see there. That's why left partition will have the 2 elements and the right partition will have the again 2 elements there if you see that. That's why left partition 6 2, right partition 9 3 again. So this is the you can say the divide and conquer uh, strategy you are applying there. This will happen recursively until the sub part is so small or too small, that will be that is a single element itself if you see there. Okay, then in second step you can say the two partitions again subdivided into two sub partitions, that is the 6 2, that is the left partition in two sub partition, that is 6 and 2. This will be the two individual partition as a single or individual element if you see that. Similarly right partition can be divided as a you can say the left partition as 9 and right partition as a 3, because it is too small and it is already single element. Okay, so you need to start combining the result again. If you see there, okay, during combining, okay, you need to take care that is the those elements should be in a particular sequence. That is the you are combining or merging or combining. You can use the function merge there, okay, in your program. So merging or combining means you are combining 6 and 2, that is the in particular sequence 2 6. Okay, in step number you can say the 3 if you see that. Then uh, right side partition, that is the 9 and 3 will be combined as a or merged as a 3 9 if you see there. So there are two combined or merged partition, that is the left and right if you see there, because you are considering results of the left partition and right partition here if you see there. If you consider the beginning partition there if you see, then finally in step number 4 you are combining the that is the this uh, merged partition in previous step, that is the 2 6 and 3 9. Okay, so that your final that is the array will be or combined or merged array will be 2 3 6 9 if you see there. Okay, so in this way merge sort work there, that is the parallel merge sort. Okay, so you have to use the appropriate parallel construct there for parallel execution purpose if you see that, so that it will you can say the execute your program you can say in a more faster way if you see that, compared to the its sequential version. Then this is about the you can say the parallel that is the merge sort algorithm, how actually it works if you see there. So you have to design its that is the parallel version, okay, in the form of the program. So we'll see that program also here, how you need to write that program for the parallel merge sort algorithm. So we already discussed its logic with the help of example. I think no need to explain it again. You need to include the header files there. For C++, IOSTream is compulsory. Then rest of header file you can add as per your requirement. Then omp.h, this is the most important header file as per as the open you can say the OMP programming is concerned. If you see there, OMP stands for open multiprocessing. That header file you need to add there. Then using namespace study for C++, then you are declaring that is the functions merge sort having int a, that is array, int I, that is the beginning index, int j, this may be the final index. Then void merge int a, so this is the merge sort, that is the partitioning the array into the sub array if you see there, that is the merge sort. And merge means you are combining the you can say the those sorted element if you see there, or sub partitions into the final partition if you see there. Okay, so merge function having the you can say the arguments you will consider here, that is the int a array will be there, int I1, int j1, that is the I1 and j1 are the starting and ending element of the left partition, and int I2 and int j2 will be the you can say the beginning element and ending element, or the pointing to the first element and the last element of the right partition if you see there, because you have to merge those you can say the sorted partitions there. Then this is the actual you can say the definition of the merge sort, wide merge sort, int a, int I, int j. A is the array, that is you have to enter the array element also, so you will see that part in the main function. Okay, here you are defining the merge sort logic if you see that int I, int j, that is I initially pointing to the initial element of the array a, and j for the last element. So you are finding the mid here, int mid you need to declare there, and if I less than j you have to find out the mid. Okay, that is mid equal to I plus j divided by 2 each time if you see that. Okay, and then you can write the your logic inside that particular parallel construct. So here you are using the parallel construct as a section if you see that. So this is the one kind of the you can say the parallel construct you are using here, hash pragma omp parallel sections. In earlier program we have seen the hash pragma omp parallel for, for shared a comma n likewise. So here that was limited to the for loop, but this has pragma OMP parallel section. So this is limited to this particular section. If you see there, okay, this section may contain the that is the iterative call also. If you see there, this process may having the different iterations. If you see there, so that is the partitioning the your array. It will continue until the sub partition is so small or too small, that will be that is the as a single array element. Okay, and that will continue until you are finding the single element in that particular sub partition, and sub partition like this. Okay, and merge opposite to this one, that is you are merging step by step. That is initially from left partition 2 elements are combined, in next step 4 elements combined. Okay, that is the left partition. Then again the right partition initially 2, then next 2, that is the 4 elements. Then finally you are combining the left sub partition and right sub partition in final step, that is the having the total 8 element as far as the your array size is 8 is concerned. If you see that, so hash pragma OMP parallel sections. So your parallel execution will start here. So here a number of threads will be created equal to the number of cores on your machine. If you see that, per core 1 thread will be created. Okay, if you see that, if it is your processor having the 8 number of cores, so 8 threads will be created, 1 per core. If you see that, if you want that is the 16 number of threads on your machine, you need to mention it, you can say the in the form of that line. Okay, if you see that, that is the hash pragma OMP parallel sections. And after that also you can use the or before that also one line you can add there, hash pragma OMP parallel num underscore threads in parenthesis 8 or in parenthesis 16. So those many number of threads will be created. That is the, if you are mentioning your figure as a 16, so 2 per core will be created. If you see that, so this will be the logic there. So hash pragma OMP parallel sections. So your parallel construct will start from this line. Okay, if you see there, again for each subsection, that is the merge sort, and you can say the that is the left partition and the right partition. You can again apply the that parallel construct again, hash pragma OMP section for the left partition, merge sort a comma I comma mid. Okay, recursively you can apply that one for the left partition, and hash pragma OMP section merge sort a comma mid plus 1 comma j, that is the for right partition. Okay, so it will that is the apply that particular you can say the approach, that is the divide and conquer to partition the given array in a sub and sub partition recursively. If you see there, okay, then finally you can call the merge that is the function that is you have defined after this particular function, mid merge a comma I comma mid. So I is the here beginning element of the left partition, mid is the last element of left partition, mid plus 1 beginning of right partition, and j is the last element. If you see that, so again once your you can say you have partitioned your element in individual elements. So that is the partition having the single element. In that case, you need to merge the left partition elements and the right partition element, as we have seen in a previous example. If you see that, so this is about the merge sort function. That is the you are dividing the array into the left partition and right partition. If you see that, okay, recursively. If you see that. And finally, you are calling the merge function. So how actually the merge function work? We have discussed that with the help of example, but we have defined it separately also here. If you see that, that is the void merge int a, that is the given array, int I1, int J1. This is the I1 starting element of left partition, J1 last element of left partition, int I2 that is the, and int J2 are the starting you can say the index of the right partition, and j will be the you can say the last element of the right partition. Okay, so initially you are taking the temporary size of your resultant array, you will take as a 1000. If you see that, so int I, j, k variables you have declared there, there. Initially you are assigning value of I1 to I and value of I2 as a j. So what is I1 here? This is the beginning of left partition. That is the first index of the left or element of the first partition, and I2 is pointing to the first element of the right partition. So I equal to I1, j equal to I2, and initially k equal to 0. So while loop you are using there, while I less than or equal to j1, j1 is the last element of left partition, and this is the logical AND operation. Okay, and j less than or equal to j2. So what is j2 here? Last element of the second partition. And if a of I is less than a of j, then you have to increment the value of k plus k. That is the temp of k plus plus equal to a of I plus plus. You have to increment there. Else, if it is false, that is the a of I is not less than a of j. Okay, in that case, temp of k plus plus equal to a of j plus plus, means in that case you need to increment the j. Okay, so this will be the you can show the merging of the partitions. Okay, if you see there, and in case of the merge function, that is the still it is continued. Logic will be while I less than or equal to j1. Okay, if you see that, so you know j1 is the last element of the left partition. So temp of k plus plus equal to a of I plus plus in that case also. And while j less than or equal to j2. So what is j2? j2 is the last element of the you can show the right partition. So in that case, temp of k plus plus equal to a of j plus plus, if you see that, because and finally you need to uh, assign the temp of j to the a of I. Okay, using the for loop I equal to I1, then j equal to 0. Okay, and I1 means beginning of the left partition. Okay, and I less than or equal to j2. j2 is the last element of the, you can say the, that is j2 is pointing to the last element of the right partition. I plus plus j plus plus, a of I equal to temp of j. Okay, if you see there, so in this way you need to the you can say combine or merge the divided partitions. Okay, which solution you have found out already. If you see that, then you need to merge it step by step. Okay, initially 2 elements combined, then 4 elements combined. Okay, from the left partition in our earlier example, and right partition also same. Initially 2 elements combined, then 4 elements, then finally in final array you can combine these 4 from left partition and 4 from the right partition. But you need to take care here, those elements should be in a particular sequence, either in ascending order or the descending order. Then you can write the main function here, that is for declaring array and entering the array elements, and then calling the merge sort function, if you see there. And then after sorting you need to display the that is the sorted elements also. So int main int pointer a, that is you are using pointer to array n I, then enter the total elements in that array, that is n, c in n, a equal to new int of n. C out, enter the elements using the for loop I equal to 0, I less than n, I plus plus, c in a of I. Then you can call the merge sort function there, which we have already discussed, a comma 0 comma n minus 1, that is array a starting index 0 and last index n minus 1. Then after sorting you need to display the array elements in sorted order, that is sorted array is using the for loop for I equal to 0, I less than n, I plus plus, c out a of I, if you see there, slash n a of I, if you see there, so that it will display the each element on a new line in that sorted array. Return 0 for this int main function. So this is all about the merge sort program. Then how to execute this program, you can see here. You can use the G++ compiler, G++ merge sort.cpp space hyphen f open mp dot slash a dot out. If first step is that is you can say the OK, G++ merge sort.cpp space hyphen f open mp. If there is no any error, then that is the compilation is successful. Then you can proceed for the execution step, that is dot slash a dot out. Then you enter total number of elements as 8 or 800 or 1000 as per your requirement. Okay, or you can use the rand function for entering the array element, and then you can get the sorted elements, if you see that. Okay, then enter elements like 2, 34, 45, 21, 8, 9, 4, 3, 8, 1. The sorted array is there, 2, 8, 9, 21, 34, 43, up to 81. So you can take the more number of elements so that you can compare your sequential version of the merge sort algorithm with a parallel version of your merge sort algorithm. If you see there, you know that is the average case time complexity of the sequential search algorithm for merge sort algorithm is uh, of the order of 10 log n, I think, right? If you see there, you might have studied that part. If you see there, average case time complexity. So you can compare the sequential algorithm time complexity with a parallel algorithm time complexity. Okay. For that purpose, you can use the particular function, time function. Okay, which will compute the execution time of your program. Okay, and from that you will understand the which algorithm is better, that is the it's a serial sequential version or the parallel version. So definitely parallel version is better than the sequential version of the same algorithm. So we'll stop here.